The work I'm going to tell you about tonight was done by many people besides myself. I collaborated with many other scientists, and I may mention, well, I will certainly mention some names as I go through this story, but I will certainly leave some out. But please don't have the impression that this is all work that I did. Many other people contributed a lot to the story. The story is about the Cretaceous-Tertiary boundary event. You're probably all aware that 12 years ago, a paper was published in Science by Alvarez's Michel and Massaro suggesting that there was a very thin layer of impact ejecta at the Cretaceous-Tertiary boundary, at the level of a mass extinction that occurred, effectively ending the Cretaceous period, causing a great change in the Earth. Something like half or 3/4 of all species that were alive on the Earth, at least in the types of macro species that we see fossils of, went extinct at that time. Many good cartoons. I think I've collected over 30 humorous cartoons about the KT boundary now. These are a selection. There's even been many political cartoons. We could take a focus on the left any time you put time on. This theory remains, it was controversial when first proposed, and it remains very controversial. And the arguments initially seem to have been somewhat been caused by, in the early years of geology, and by early years I'm speaking, say, from Chaucer's time, or about 1100 till about 1780, the people who tried to figure out how the world was made believed in catastrophism. They believed in a biblical deluge or events of that type. And so when fossils were found on the tops of mountains, or they found obvious quartz deposits in the sedimentary record with a jumble of things, they thought something very catastrophic had happened. And in 1780, James Hutton started the theory of uniformitarianism, which suggested that processes we observe in the current world are responsible for all these layers of rock, which you see, and of course slow processes of mountain building are what elevate the marine sediments to the tops of mountains and so on. So there's nothing incredibly dramatic or catastrophic in the Earth. Geology, after believing there were catastrophes, switched over to steady state uniformitarianism with no catastrophes. And that theory, in fact, served us very well, because most things in geology are not, in fact, catastrophic. What the Alvarezes were proposing was, in fact, a very catastrophic process, though. And many geologists, especially paleontologists, still don't like it. As a matter of fact, I could point out to you a half dozen papers in the literature of, say, the last 3 months saying that there's absolutely nothing to anything I'm going to talk about tonight. And it's a puzzle to me, in fact, why this debate has gone on so long and so bitterly. I mean, it's literally gotten to the level where we can go into the field, I can point at this rock and say it's one thing, and other people will point to it and say it's something else. Suffice to say that I think we now understand that there was a large impact at the Cretaceous-Tertiary boundary. I should say this story really started in 1687, when Isaac Newton published his Principia, in which he showed that comets, rather than being phenomena of the upper atmosphere, of course Tycho Brahe had already demonstrated that comets were far away from parallax arguments, but Newton showed that they were objects which described parabolic or elliptical orbits about the sun. And very soon after the realization that comets crossed the Earth's orbit, I think it was Halley who first suggested that once in a while a comet should bump into the Earth. There should be impacts. And in 1750, the French astronomer Democritus suggested that the impacts of these comets might cause extinctions of species, mass extinctions. So the intellectual underpinnings for what the Alvarezes were later to suggest are very old, in fact, predate uniformitarianism. In 1980, many people said, okay, look, you said there's this great big impact. and you're showing me this very thin layer of clay in the rocks as evidence. If there is a big impact, there has to be a big crater somewhere. There should be thick ejecta deposits close to the crater. There should be, if it's in the ocean, there should be giant deposits made by the huge waves washing ashore and so on. And all I'm seeing is this thin clay layer, so I don't believe you. When I went to start my PhD work in '84, I got interested in this problem and effectively set out to find these proximal deposits and the crater. And what I'm going to tell you tonight is how, in fact, we did find the crater. Next 2 slides, please. So, why do we think there's a large impact? This slide lists the main reasons. There's this thin layer about the globe, all over the globe. The platinum group elements occur in chondritic proportions, and the proportions in which they're found in meteorites, which is unlike, for example, how they come out of volcanoes. There are shock mineral grains occurring globally in the layers. There are tectites near the source craters. Tectites are produced in impact events. And the largest known impact crater on Earth possibly occurs at the KT boundary. There were a number of clues that suggested where the crater might be, and I will now go through these 5 reasons on 5 lines of evidence leading to the whereabouts of the crater. This slide was taken from Ellengrab in Austria. There's a shelf of rock coming out of us here, that's why it's out of focus. This coin is about the size of a quarter. This rock represents the uppermost Cretaceous marine limestones. If you look at a thin section of this, from just this position, you'll see it's full of all the late Cretaceous microfossils. And then this 2 millimeter thick rusty clay layer occurs. This is the layer that occurs globally at the KT boundary. It's high in iridium and other platinum group elements. It has shock quartz, has other unusual minerals which are not commonly found in the terrestrial environment. Above it, in the base of the tertiary, most of the Cretaceous fossils are gone. You can literally shave off the millimeter of sediment below it and compare it to the millimeter of sediment above it, and most of life is gone. Certainly you can find places where there's been mixing. You can find worm burrows that have brought one sediment up and down and the other, but if you do this carefully, you will see that about 50% of the microfossils that lived in the late Cretaceous oceans are gone. This slide is from the Woodside Creek locality in New Zealand. Again, this is a shelf of the latest Cretaceous limestone, and this 2 millimeter thick rusty layer represents precisely the same bed, even though it's on the opposite side of the Earth. And again, here's the base of the tertiary. So this represents the globally distributed layer. It's uniform in thickness all over the globe. Clearly, something very extraordinary happened to produce a thin layer all over the surface of the Earth. And this is what I call the fireball layer, implying it was dispersed by the impact fireball. Next slide, please. Now, this is a slab showing the layers in the non-marine sequence from near the Colorado and New Mexico border in western U.S. This layer from here to here, which is about 3 millimeters thick, represents the fireball layer in this sequence. The uppermost Cretaceous mudstones are here. They have uppermost Cretaceous spores in them. And then above the fireball layer, you're into the tertiary. Again, a mass extinction and a massive ecological disruption has occurred. This layer is rich in iridium and shock quartz and so on. However, in this part of the world, there's an extra layer. You see this layer from here to here, which is about 2.5 centimeters thick. This represents something additional. The 2 layers were discovered in, let's say, 84 and 85, and very early someone, Jan Smit, suggested that the presence of this extra layer probably indicated that the impact site was somewhere in this part of the world. And it turns out that at all of these triangles in circles in this map, this extra layer, what I call the ejecta layer, also occurs. And so clearly you look at this and say, well, gee, we've got an extra layer in this part of the world. It doesn't occur in Europe, it doesn't occur in Asia, it doesn't occur in ocean basins elsewhere, the southern Atlantic, the western Pacific, it doesn't occur in New Zealand. The impact site's got to be somewhere near here. This is a very simple argument. Next slide, please. This shows this ejecta layer from a deep sea core off of New Jersey. This shows the ejecta layer from a boundary site in Wyoming. This is non-marine, this is marine and deep sea. And in these slides, this is the uppermost Cretaceous. The ejecta layer stays here. You can see it's spotted. At these localities, the ejecta layer is composed of 0.5 millimeter to 1 millimeter pellets. And in 1988, it was suggested that these represented altered tectites. Now, a tectite is a natural glass produced in impacts. Because of the great specific energy of a projectile when it hits the Earth, it's able to vaporize and melt the target rock. The melted rock is thrown out of the crater up into the air and of course cools, but it cools quick enough to make glass instead of crystalline rock. And these glassy beads rain back down onto the Earth. And there are 4 known tectite strewn fields of comparatively young age scattered about the surface of the Earth, where in some cases we know where the source crater is, and you can observe the changes in tectites as you go away from the crater. The word's derived from the Greek tektos, meaning melted. And again, in this deep sea core, you can see that the ejecta layer is spotted. And again, there are these approximately 1 millimeter sized pellets there. And so early on, we suspected that the ejecta layer was composed of altered tectites. Although this was controversial too. Everything about the KT boundary is controversial. Next slide, please. So, at this time, for geochemical reasons, which I won't go into, I thought it was likely that the impact had occurred in the ocean basin. There are 2 kinds of crust on the Earth, oceanic crust and continental crust. And the bet was from analyzing these layers, which were completely altered to secondary minerals, generally clay minerals, it was thought you could tell the difference between a source of continental crust versus oceanic crust. This actually turned out to be wrong. Nevertheless, believing it was an oceanic impact site, I started looking for descriptions of deposits that might have been disturbed by giant waves at the boundary. You appreciate the ocean's about 4 or 5 kilometers deep on average. And if you have an impact of a 10-kilometer asteroid or comet into an ocean that deep, the waves created are going to be huge. Once they settle down from the actual ejection process, there's going to be a wave as high as the ocean is deep propagating outwards. In other words, a wave 4 or 5 kilometers high. Obviously, it shrinks with distance, inversely proportional to distance, but when it washes up onto the edge of the continents, it's going to be spectacular. And it turned out such a deposit had been described as early as 1981 here at Brazos River, Texas. And in fact, after looking at more of the literature, all these squares represent localities where such coarse deposits have been described or studied at the boundary. And again, they don't occur anywhere else in the world. You can go to Europe, you don't see them. You can go to Asia, you don't see them. You can go to New Zealand, you don't see them. So again, you say, well, the impact site must be somewhere near here, and it looks like from this distribution it's falling to the south of North America, maybe between the Americas. And as an example of one of these coarse deposits, this is the Brazos River, Texas locality, which is here. This outcrop is routinely covered with river mud. I'm almost standing in the river as I took this photo. And this brown stuff at the bottom is the river mud. I spent 2 days shoveling off the outcrop, which you have to do every year. And then you wash off the mud to get photographs like this. This is the Cretaceous mud. This is a shelf. The water is about 125 meters deep at KT boundary time. And it's full of late Cretaceous fossils. Then there's an erosional surface that's hard to see because there's gray rock on top of gray rock. But then there's a coarse deposit, and you can see there's a boulder here in this coarse deposit that's about 1 meter across. So something happened here that could erode the seafloor in 125 meters of water depth and transport boulders this big. then there's a fine upward succession, and eventually up near the, oh, we're having a technical malfunction here. That's because I'm pointing the laser into my hand rather than a board. Here is the layer where the fireball layer occurs. This is the iridium peak just there. So we have, again, you know, the fireball layer that's always present, but at this site, there's this extra quartz deposit occurring below it. Next slides, please. It turns out that in Cuba, you have the most spectacular possible impact wave deposits described. Tectite published this in '86. He described a single graded bed, that means it was deposited in a single event, up to 450 meters thick, or about 1,500 feet thick, with boulders at the base up to about 5 feet across at the Cretaceous-Tertiary boundary. And at the time, he thought it was due to a seismically triggered slump, but he did mention the possibility it could be due to an impact. And I felt it was very likely that from the distribution of the ejecta layer and the impact wave deposits, that the impact site had to be somewhere in this part of the world. But this turned out to be a very unpopular idea, and I was unable to get it published. So what more can you do to test this idea? Now, one consequence is the ejecta layer was about an inch thick in western Canada and in the western United States. If the impact site is, in fact, between the Americas, then in the Caribbean regions, the ejecta should be much thicker again. And there had been a deposit described in Haiti by Florentine RASC. He had described a deposit about half a meter thick at the Cretaceous-Tertiary boundary, which he thought was volcanogenic, had been produced by a volcano. And so I eventually visited him, and within seconds of seeing his samples, I knew that it was a thick ejecta layer because the altered tectite shapes were very obvious and very large. And eventually, I was able to travel to Haiti and study these rocks in the field. This was in early in 1990. Next slides, please. And this is what this layer looks like close up. This was deposited in a deep sea environment, say greater than 2 kilometers water depth. These are the late Cretaceous limestones, again, full of all the late Cretaceous fossils. These are the base of the Tertiary. Again, the mass extinction has occurred. The Cretaceous forms are gone. And at the boundary, there's a layer that goes from here to this site. It's 46 centimeters thick. And this represents the ejecta layer, which was 2.5 centimeters thick in Colorado. Well, obviously, it doesn't take a rocket scientist to figure out that we've got to be a lot closer to the impact crater with the ejecta so much thicker, and the impact site must be somewhere near here. And with this discovery, people finally started taking this idea seriously. This is a hand specimen from the top of this layer. This olive brown stuff is the ejecta material. And right at the top of it, you can see about a centimeter thick wispy grayer layer. This is the fireball layer as it looks in the deep sea. It's mixed up by fine-scale bioturbation, so it's made a bit wispy. But when you analyze this, you get your maximum abundances and elements like iridium and so on, which are enriched in that layer. In fact, these dark bits you see here are worm tubes. Immediately after the layer was deposited, worms brought the less diluted material down and mixed it into the upper part of the ejecta layer, so it wasn't stirred up by the fine-scale bioturbation. So again, you have the same stratigraphy. The fireball layer on top, a very thin layer, same composition, and an ejecta layer underneath, only the ejecta layer is much thicker. So all of a sudden, we were off to the races, and everyone rushed to the Caribbean region to try to find more sites and so on, and things started moving very quickly since 1990. Next slides, please. I said this layer was completely composed of altered tectites. If you could please try to focus on the left slide here. The matches for scale, you can see that these shapes are indeed mostly spherical, but you have dumbbells and elliptical ones, irregular shapes, confused examples, all the classic shapes that you get in tektites and microtectites. And it's, it's trivially easy to go into the field and pick these out of the rock. And the best arguments are the simplest ones. Most people agree that sure enough these were tektites. It also turns out that this layer has abundant shock quartz in it. This is the first slide of showing shock quartz. A typical grain of quartz will be somewhat colorful, but it won't have any of these lines. These lines represent dislocations in the crystal structure caused by the shock wave passing through the grain of quartz. They occur in a predictable manner and a predictable orientation in the crystal. And there are 10 times as many shock grains in this layer in Haiti. And there are, next slides please. There are also larger shock quartz grains than anywhere else. This particular grain is 1.25 millimeters across. The one I just showed you was about 1/3 of a millimeter across. Because I pulled back so much in the microscope, you can see the lineations, but not as well as in the close-up. Another argument for saying that the impact site has to be in this part of the world is that in the other parts of the world, like in New Zealand, you're only getting grains 0.1 millimeters across. In Europe, they're 0.1 to 0.2. In North America, they're about 0.5 millimeter, and of course, at Haiti, they're bigger still. They're 1.25 millimeters across. So we have this gradient in shock quartz grain size, which also suggested the impact site is somewhere in this part of the world. Next slide, please. Now, it fell to others to discover that at least 3 other groups independently made this discovery, that some of these altered clay pellets contained unaltered Tectite glass in their centers. And finding this unaltered Tectite glass was great simply because it removed a lot of the doubt. I mean, some people said, again, well, how do you know these are Tectites? I mean, once you have the unaltered Tectite glass, your case is much better. And it turns out that the alteration that turned this glass to the clay changed its composition a great deal. If you analyze this clay from the trace element compositions, you would, I did say it was from oceanic crust, but it turns out that glass, although it's a bit unusual in composition, is definitely from continental crust. And so, that told us very clearly the impact was on a continent, it wasn't in an ocean. This is one of those spherules broken out. You can see it still has its spherical shape. Next slides, please. Now, this is a plate tectonic reconstruction at KT boundary time, or 65 million years ago. This is the southern part of North America. This is the Yucatan Peninsula. There's the Gulf of Mexico. There's Florida. Here's South America. It's been quite active in the last 65 million years. This is the southern peninsula of Haiti is reconstructed, and that's the Balak Haiti site, which I showed you slides of. Since then, a couple of other sites have been published on. There's one here in northeastern Mexico called the Limestones site, and one here in deep sea cores, DSTP 540 in particular, where we also see thick ejecta. And I'll talk just briefly about Limestones. Next slide, please. I should say that the Limestones site was found by Jan Smit, Sandro Montanari, Walter Alvarez, and Nicholas Swinburne. And this is a slide showing the Limestones site. Again, this is the uppermost Cretaceous rock. And this represents the same bed as preserved in Haiti. Here it is all current lineated. This site is on the continental slope. The Haitian site was in the deep sea. The Brazos River site is up in the shelf. This site is on the slope that goes from the shelf to the deep sea. And so the impact waves apparently washed some of these, the ejecta or tektites, off the slope and deposited a current bedded layer. Okay. Now, it turns out that at the Limestones site, again, you can see this rock is spotted from the tektites. The ejecta goes from here out to about there. It turns out the Limestones locality also preserved an altered Tectite glass in the centers of these altered tektites. And quite a range of compositions. This sort of dark brownish green glass is the same as you get at the Haitian locality. But you can see you also have reddish glass, you have clear glass, you have yellow glass. And on the Haitian localities, some of this yellow glass was preserved. It's very calcium rich, suggesting the impact hit a limestone terrain. Layers of limestone covering the normal silicate continental crust. But you also have high potassium, suggesting there were what we call evaporites or gypsum in these layers. And so having all these different compositions of glass, again, tells us a lot about what the impact site must be like. Next slide, please. So, when I first found the Haitian site, this is another plate tectonic reconstruction, I was thinking that the impact must be in the deep ocean. And I found something here in seismic reflection records in the ocean floor that looked like a circular basin that could be an impact crater. I knew what distance to look for a structure from Haiti by using an ejecta scaling relation. There's formulas that describe, given a certain size of crater, how the ejecta thickness declines with distance. Of course, having an ejecta deposit and assuming a size of the crater, you can calculate how far away the crater should be. And we knew at least the ballpark and what the size of the crater should be on the basis of, smaller craters don't make mass extinctions and can't be too big because there aren't 1,000-kilometer craters on the Earth or other terrestrial planets. And so the guess was it should be a crater about 200 kilometers in diameter. And using that, this dashed circle shows the calculation. The crater should be somewhere on this line. And this was the only candidate I could find in the deep sea. Though it turns out there was another structure here in the upper canyon, which we'll be talking much more about later, which turns out to probably be the Haiti boundary crater. But I'll point out that our guess on the distance from Haiti turned out to be pretty good, even though we had the wrong kind of crust. Now, we have these three different sites. I'm going to ignore the existence for this crater for a moment and show you how you can calculate how big the crater should be and where the crater should be now that you have three sites instead of just one. Next slide, please. I'm going to show you just a little bit of theory and a perfect case to start with. This is just a geographic grid. These stars represent two ejecta localities of an equal thickness. You can assume a radius of, say, 40 kilometers, and you can calculate how far away a 40-kilometer crater should be from this ejecta site. You can do the same thing for this one. You see that these two circles don't overlap. Therefore, the crater has got to be bigger than 40 kilometers. So you can try 80. You draw this circle, you draw that circle, and indeed they intersect here or here. So an 80-kilometer crater at either of those points could produce this ejecta distribution. And you can continue this process and get circles which intersect, and you'll see that they intersect in such a way as they define the circular locus of solutions. In other words, the smallest possible crater is right between the two, the biggest is over here. So with two sites, you can calculate a range of locations and sizes. Now, we're going to look at this with three sites. And this is just a model crater to show how the theory works. These are two sites, and this is the solution circle. So the only circles I'm going to show you now are solution circles. And I'm going to keep this simple, so just bear with me and watch what the circles do. Next slide, please. It turns out that once you have three sites, you can narrow down the possible solutions a lot. This is the solution circle once you bring in a third site, and it brings in this pair. You can see instead of having this whole possibility, you only have two solutions, one right there and one right there. And this simply brings in the third circle of the other pair to show you it does the same thing. So once you have three sites, there's only two possible solutions, here and here. To get a unique solution, you need four sites. Next slide, please. Now, this is reality. This isn't fudged model data like you're looking at. This is DSTP 540. This is Haiti, and this is Mimbrel in Mexico. These are the actual observed thicknesses. This is the actual location of this crater I'll be talking about. And you can see with three sites, the predicted location is either here or there. And once you bring in a foresight, in this case a site way up here in Wyoming off of this grid, this additional solution circle is this one here. So you can see that bringing the foresight says that that is not correct, and indeed this is the correct solution. And it works out remarkably well. Next slide, please. Now, there's about a dozen sites, and once you get into the circle business, all of a sudden the circles all over the place. I mean, it gets complicated in a hurry. So on this graph, all we've plotted are the intersections as points, and we've blown them up. So this is the actual crater I'll be talking about, and all of these points represent the intersections of the solution circles. And you can see they concentrate right here. They're spread out in this direction a bit because a lot of the sites are up this way, and the tangents to the circles mean that they spread out that way. So you're predicting a crater about there. Next slide, please. Now people say, well, this is just luck. I mean, you were lucky this time. It doesn't really mean anything. So what I've done here is I've deliberately doubled the thickness there, and I have the thickness here. I fudged the data to make it bad, to see how far away the predicted solution is going to be. And because the distance is proportional to the cube root of the thickness, it means that you're always going to come out pretty close with just factor of 2 variations. You're not only going to be off about 25%. You've moved here a couple of crater diameters to the north, but not far. So the bottom line is the method is quite robust, and you're looking for something that has to be in this area. Next slide, please. Now there's another thing you can do, which is assume that this crater is in fact the crater. I named it the Chicxulub crater, and I'll call it the Chicxulub crater now. Assume the Chicxulub crater is the KT boundary crater. It's 180 kilometers in diameter. Calculate the predicted thicknesses of ejecta with distance away from that crater. Here you see them on a log-log plot, thickness versus distance. Here it's log linear. This is the same curve. This is the predicted thickness of ejecta, and all these dots are the actual observed thicknesses of ejecta. And you can see that indeed, over 5 orders of magnitude of variation in the thickness, the observations match the prediction very well. This is an upper limit. There's a good reason for why that particular point is low. So you say, well, this is pretty remarkable. I mean, things fit pretty well. And you can inverse this. You can say, well, let's do a least squares fitting routine to the data and see what size crater is predicted at Chicxulub's position. The best 7 points predict a crater of 178 kilometers diameter. Using all the data, you predict a crater of 196 kilometers diameter versus the 180 kilometers diameter observed. And as a final check, you can calculate the volume of the ejecta in this blanket and compare it to the volume of the Chicxulub crater. And these two volumes match as well. Next slide, please. So what this has done, you've predicted, you're looking for a crater 180 to 200 kilometers across, and you predicted it's going to be on the Campeche bank. This is the outline of the Yucatan Peninsula right there. And you were predicting a crater right about here, and it has to be within this area. This colored map is showing the Bouguer gravity anomaly. The different colors correspond to intensities. And it also has shading in it to bring out structure within the gravity data. It's the horizontal gradient of the gravity data have been shaded. And as I assume it's apparent to you all, there's a very spectacular ring structure right here. There's the outer ring, a middle ring, and an inner ring. And the northern third of it is a bit truncated. And I mean, as soon as I saw this, it seemed very likely indeed that this was the big crater. It had been suggested to Pemex as early as 1968 by an exploration geophysicist named Balthasar, when he looked at the gravity data here, that this might be a big impact crater, and nothing ever happened to it. Pemex controls all of the petroleum exploration data in Mexico, and it has been very difficult to get much data out of the country, and of course Balthasar tried to get data released and could not. Then later in 1978, Glenn Penfield was doing an aeromagnetic survey in this area, and he found a spectacular magnetic anomaly in this region and asked to see the gravity data and saw indeed a spectacular negative gravity anomaly as impact craters happen. So he thought it might be a crater too, and Pemex let him and Antonio Camargo publish an abstract about this in 1981, but they wouldn't release the data so that they could do a paper about it either. And in his presentation in 1981 at the SEG meeting, he actually suggested that this might be the KT boundary crater. And if Pemex had released the data to them so they could do a paper at that time, the KT boundary debate may have been much shorter, but they didn't. And so after a couple of years of trying to find samples to confirm this, Glenn sort of gave up and didn't do much more to it until I came along in actually 1990 looking for craters in this area and learned of his work from a newspaper reporter who had covered his original presentation in 1981 and contacted him, and things started on. By the way, this is the Bouguer gravity anomaly without the gradient. The blues are lows. This just shows indeed it's a negative anomaly and it's truncated in the northern third. Next slide, please. So why do we know that the Chicxulub crater is a crater? Its shape. It's a circular hole. The gravity, it's a multi-ring negative anomaly, just as you expect for big craters. You find evidence of shock metamorphism in the rocks there. We got lucky and we were able to locate some samples from petroleum drilling that had been done there starting in the 1950s. And the stratigraphy recorded by the oil wells was a breccia melt rock sequence exactly as you predict for a crater film. Next slide, please. We were very lucky to find some samples because the Pemex cores and chip samples and so on were stored in the central warehouse facility that burned down in 1981, and all this stuff was lost. So we found some bits that had been sent previously to other researchers for other purposes. This is the coast of the Yucatan. This is the same Bouguer gravity data in a contoured format, and this is the crater drawn in. And these are the drill holes within the structure. There are 3 deep drill holes. These 2 dashed lines here show gravity profiles across the structure. This is the regional gradient, which I have not removed. This is the gravity anomaly across Manicouagan crater in Quebec, which is a 90-kilometer diameter crater. I stretched the horizontal scale and the vertical scale a bit so they're comparable, but you can see that there's a double peak high in both. There are 2 lows in both. In other words, the shape of the gravity anomaly matches very well. Next slide, please. It's also true that because of the brecciation, craters have a mass deficiency. The density of the rock is lowered by breaking up the rock and having pore space in between them. And you can plot the diameter of crater versus the observed mass deficiency and get sort of a straight line. And it turns out the Chicxulub lies in a straight line. So again, the total mass deficiency is about what you expect for a big crater of this size. This is just to say that the magnetic data over the crater are also very spectacular, but they have not been released in any form yet by Pemex, and so they cannot yet be shown. But suffice to say, there's a central zone of very high magnitude anomalies, which is circular, elongated a little bit in the northwest direction. And the magnetic anomalies are not truncated by whatever truncates the gravity anomaly, so it's a completely circular structure. Next slide, please. So these are stack columns from these 3 oil wells inside the crater, and I've arranged them with distance to the center of the crater. The center would be, 15 kilometers this way. These are meters in terms of depth. There's tertiary fill, limestones, shales, marls, lying on top of breccias, and then andesitic glass and andesitic crystalline rocks. And over from this hole, the Yucatan 6 hole, we were able to find some samples of core at 2 different places, here, 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 and here. I mean, the samples came from 2 different sources. And it turns out that this sample, N14, in what was mapped as a sandstone, but which turns out to be a polymic breccia. Next slide, please. This is the N14 polymic breccia sample. You can see it's not a sandstone. It's composed of angular clasts of variable sizes of different lithologies. It contains both what look like melt droplets that have been altered to a very poorly ordered silicate. And next slide, please. It contains shock quartz grains. This is a shock quartz grain, not breccia. About a third of the quartz grains separate from the breccia are shocked. Again, the shock lamellae are in the appropriate orientations and so on. And if you do a Debye-Scher X-ray diffraction study of the quartz grains, a typical quartz grain looks like this, one that has no damage to its crystal structure, so that the diffraction spots are very sharp. Damaged crystals tend to smear out those spots. It's called streakiness. And by calibrating the level of streakiness, you can say what the shock level is, and it's 10 to 20 gigapascals about in these three quartz grains. Next slide, please. Now, below the N17 rock, we had one rock, below the N14, we had this N17 rock, which is from the microcrystalline andesite. Turns out it's not a volcanic andesite, it is a melt rock. It's about 25% inclusions, pieces, crystals, and rock fragments that have been cut up in a melt and not completely digested. And some of them are shock quartz as well. And it has very unusual chemistry for an andesite. Melt rocks and craters are like that because you've melted whatever is there and mixed it all together. Next slide, please. These are the three holes inside the structure. There are several holes outside it, and it turns out that in one of them, and by the way, note here that the Cretaceous is greatly depressed. Here's the KT boundary, and it's way up there outside. This means there was a basin here at KT boundary time, or a hole, as if you had a crater. And also notice that on top of the breccias here, there's some upper Cretaceous recorded. There are actually about 100 meters of limestones in this basin, which had been logged as late Cretaceous. And you appreciate, if the crater was of KT boundary age, all the rocks filling in the hole would have to be tertiary in age. This is a critical point for trying to determine the age of the crater. We get hold of one sample from this limestone, this unit that had been mapped, logged as late Cretaceous above the breccias, and two different paleontologists independently placed it as P3, or late Paleocene, in the tertiary. So that meant that the original age assigned to that rock was wrong, and it could very well be that this was indeed all tertiary. But that remains unproven, and to know the age precisely in the crater, you're going to have to go back and rebuild to get more samples. Now outside, in one hole, the Ejecta 2 hole, there was a 90-meter breccia recorded as the uppermost Cretaceous deposit. And it's only about 50 kilometers from the edge of the crater. Of course, the ejecta should be very thick if you're only 50 kilometers from a 180 kilometer diameter crater. And so I thought this might be the ejecta deposit. And from studying it, we found shock quartz in it. And in this case, this is a clast of ejecta, this contorted thing with a margin like that. It's a big blob of glass that's been thrown up in the air. Hasn't been shaped nicely like a tectite. It's more like a cow patty that's been flown up in the air and gushed around. It fell down in the water. This platform was covered by a shallow ocean of KT time, and it has, all the glass has been altered. You can see the internal contorted structure and so on. But it's about 2% grains of quartz and feldspar, again, which are shocked. And the fact that this breccia occurs at the KT boundary, again, is consistent with the crater having a KT boundary age. Next slide, please. Oh, this is a slide showing the shock quartz. It's not very big, so I wouldn't even bother trying to focus it. You've already seen what shock quartz looks like. Next slide, please. And it also contains shock feldspar. If you could try to focus on this one, please, Rob, you'll see that this feldspar also has shock lamellae in it, but it's generally sort of more contorted and disorganized than the quartz. And these are Debye-Scher patterns of the these feldspars, again showing that the diffraction spots are streaked. And again, you can estimate the amount of shock these feldspars have suffered. Next slide, please. So, the conclusion is that this happened on the Yucatan platform 65 million years ago. You can calculate the projectile was probably a comet based on the size of the crater and the amount of iridium that's found in the ejecta worldwide. Knowing the amount of iridium, you can calculate that a chondritic asteroid would be about 6 kilometers across, whereas comets, with all their ice and carbonaceous phases, have much less silicate, something like only 5 or 10% of the total mass. So with a comet, you can get far more of a bang for your iridium buck. Comets also travel faster than asteroids. And of course, a long period comet, the average impact speed is nearly 60 kilometers per second, whereas for an asteroid, it would only be, say, 20 kilometers per second. So because of the v-squared term and kinetic energy, you can again buy a lot more energy from a comet than you can with an asteroid. And it turns out Chicxulub took about 10 to the 32 ergs of energy to make. And you just can't do that with any plausible asteroid. It's much more likely it was a comet. Next slide, please. So, you can make a pretty good case, I think, that there was an impact at the KT boundary. I'm just going to say briefly, how could such an impact cause extinctions? Of course, you can just simply say, well, gee, 10 to the 32 ergs of energy, that's a lot of energy. It's 10,000 times all the energy in the world's nuclear arsenals, for example. And people think that if we set off all our bombs at once, it would be bad. But what about specific mechanisms? And these are the extinction mechanisms I think were probably most deadly. We know there was a dust cloud, a global dust cloud, simply because this fireball there occurs all over the Earth. And that fine-grained dust was up there in the stratosphere, and the surface of the planet was probably pitch dark for 2 or 3 months, depends on what dust settling model you particularly like. And obviously, that would make it cold. And that in itself would be bad, but I mean, obviously, some things that, for example, live in the ocean, the ocean's temperature is not going to change, and one hemisphere is always in winter anyhow, so it may not be as deadly as some things. I think that acid rain was probably the biggest killer, and this is an intent to show the world after the energy released by the impact and the re-entering ejecta burnt enough of the atmosphere to burn the nitrogen with the oxygen, make nitrous oxides, and give you a nitric acid rain pulse. Next slide, please. There's also an interesting effect. Most of the KT effects are pretty quick. The darkness lasts 3 months, and acid rain pulse will last a couple of years. But because you happen to target a very thick limestone layer on the Yucatan platform, there's a long-term effect. McLean had advocated that the Deccan basalts, which erupted about KT boundary time in India, might have caused the extinctions by releasing enough CO2 into the atmosphere to cause global warming, change the climate, and so on, change the pH of the surface layer of the oceans. And the point here is that anything that Deccan can do, Chicxulub can do better. He calculated that the flood basalts would release about 2 times 10 to the 19 grams of CO2 in a million years. But O'Keefe and Ahrens in '89 had suggested, just as a model, that if you shock a thick carbonate target, you release its CO2, and if you have a thick target and a big crater, such as the Chicxulub crater, you can release the same amount of CO2 in about 30 seconds, a trillion times faster than the Deccan can do. So obviously, with the slow release, such as at the Deccan, geologic buffer systems can precipitate CO2, so it doesn't have a big effect. Obviously, Chicxulub would have a much more catastrophic effect, and the greenhouse effect here would be sufficient to raise global temperature, say about 10 degrees C, for a time scale of something like 10,000 to 100,000 years after the impact. Additionally, it turns out there are these evaporate beds interbedded with the limestones in the Yucatan platform, and evaporate CaSO4, and by shocking that, you release SO2. And in fact, you release enough SO2 to make enough sulfuric acid to even overwhelm the acidic effect from the nitrous oxide. So you can acidify the entire surface layer of the ocean and so on. So it seems that Chicxulub, aside from being a very big impact, was also very deadly from its target type. There's only about 5% of the Earth's surface that's covered by a carbonate target this thick. The Chicxulub impact, an impact of that size, is only going to happen about once every 200 million years. The consequence is, you add those two things up, this may have been the deadliest impact the Earth experienced in, say, the last 4 billion years, or since the end of the period of heavy bombardment. So, I mean, the point is, we can imagine lots of ways to kill things. Now that people realize that Chicxulub is where it is, of course, everyone's been rushing to Mexico to look at the nearest KT boundary sections you might find to the crater. And they're in southern Mexico and Chiapas, and they're in Guatemala. And this has become quite a cottage industry. Suffice to say, some very interesting KT boundary sections have been found, and there's one very interesting wrinkle here that ties in, I don't know, archaeology with this study. A woman named Hachula Mohali Nagy was typing the obsidian artifacts at Tikal as part of the project down there. She was working there in the late 60s and 70s. And out of all the obsidian artifacts, she noticed that there were 10 nodules which were different. And we're talking tens of thousands of obsidian artifacts. And of course, they studied the obsidian. There's 9 different types. They figure out where the quarries are. They figure out the trade routes and so on. And these 10 nodules were different. And she once looked in a shop window and saw some Indochinite tectites and said, my nodules look like tectites. And started investigating them a little bit. And some things about them, their lack of crystals, their apparently low volatile content, made them look a bit like tectites. They published one abstract about it, and they stopped working on it because the petrologist she was collaborating with thought they probably weren't tectites. And it turned out, by the way, that these tectites were andesitic in composition, as the tectites in Balak-80 are andesitic in composition, the Mimbral tectites are andesitic in composition, the melt rocks of Chicxulub are andesitic in composition. So naturally, when I heard about this, I was intrigued. I got samples from her, the 3 extant ones she had brought from Guatemala in 1974, and started studying them, and it turns out they are indeed tectites, though we have not yet measured their age. So, just a couple of months ago, I went to Guatemala to do some field work looking for KT sections and to try to see the other of these nodules in the storeroom of the bodega at Tikal. And if some of you have been here, you'll recognize this view as the view from the top of Temple 4, looking out over the city to the big temples and so on. It's a beautiful place, a must see. Next slides, please. These are the 3 nodules. These 2 are from the same nodule, which we're working on, which Hachula had brought out with her. This is a centimeter scale. You can see this is sort of a teardrop shape. They're little nodules, sort of tectite shapes. They're pitted, as tectites often are. And they weren't found in the religious centers or in tombs of the wealthy. They were found in ordinary locations, ordinary dwellings or construction field. They weren't venerated in any way. It was as though someone, kids had gone out and picked up this glass and carried them home. The Maya had no glass-making technology, hence, of course, why they traded obsidian so widely. And it was an unusual thing of them. Many primitive peoples have lugged tectites around. In Australia, the Aborigines did it. In Czechoslovakia, the Stone Age man carried around the moldavites and so on. So this is not at all an unusual thing. Next slide, please. And so we worked in the storeroom and we looked at all the obsidian they had still in the storeroom, which was an incredible afternoon of digging through all these obsidian artifacts, which I assume are worth a great deal in the black market somewhere. But unfortunately, we couldn't find the other nodules. But this goes to show you can end up in some odd corners in your research. Next slide, please. So, here is what the south coast of Proto, Texas may have looked like 65 million years ago with a giant wave bearing down on it. It turns out the KT boundary was so puzzling because the people who liked an oceanic impact like myself, I mean, we were seeing things we thought were impact-based deposits. The people who looked at shock quartz and so on were saying it was a compliment because they saw shock quartz. We fought each other for many years. It turns out we were both right. The Yucatan platform is continental crust, but it was submerged at KT boundary time. And this throws some wrinkles into how do you make big waves, but you can still do it. But suffice to say, it was puzzling because the isotopic signature of the rocks there is unusual. It was an unusual target in that it was continent underwater. It really threw us a lot of curves. And as for the dinosaurs, current paleontological information suggests that they may well have made it to the boundary and been wiped out by the impact. And of course, it would be fascinating to see what they were like and how they lived, but if they hadn't gone, we probably wouldn't have evolved. So maybe for us, it was in our best interest to really change the course of evolution, and it's better to go with a bang than a whimper. Thank you.
20 years ago, Dewey McLean was dead set against the idea that Dale Russell and Wallace Tucker had of this nearby supernova causing extinction. And then 15 years ago, he came here to Ottawa for these workshops that we had in the museum.
The
K-Tech workshops. And he argued very forcefully against Louis Alvarez, Walter Alvarez, and various people who come up argue that case. Now, as you mentioned in the beginning, I'm continually seeing papers that at least argue in good referee journals that the iridium content of the KT boundary can be produced by some forms of volcanism. And I suspect these people might also argue that extremely energetic volcanic eruptions, typical of what is seen in the Central American region, might produce shock materials thrown up into the stratosphere. How do these people maintain their credibility against the sort of evidence that you presented tonight?
I mean, they would say that this Haitian layer is not impact stuff, that those are not tectites. They were produced by a volcano. I mean, the papers have just come out asserting that, in fact. They would say that this is not a crater. These are volcanic rocks. I mean, it's simply, it approaches solipsism. Anything you say, we will say the opposite and publish the opposite. And I'm trivializing it a little bit. For example, the tectites have a number of properties. And conventional tectites were high silica, obviously shaped glassy. They were relatively bubble-free. They were very dry. Tectites only have about 100 ppm water. They have reduced chemistry, reduced iron, for example, and so on. There's a number of petrologic characteristics. These Haitian tectites, or the KT tectites in general, are strange. They're andesitic in composition, which means they're not silica-rich. In this case, there was a target hit that wasn't silica-rich. And so it doesn't disturb me much to see a change because we hit different kinds of rocks. Obviously, hitting limestone and making calcium-rich glasses isn't a surprise either, but that's very unlike traditional tectites. I mean, that's the first sort of thing they'd say, well, they're not tectites by that definition. The second thing is they are very dry. Everyone agrees. However, unusually, the iron in them is not particularly reduced. And so they seize on this fact that the iron doesn't fit, therefore they're volcanic, they're not tectites. And, we would say, well, gee, this is interesting. We've expanded the envelope of tectites and how they form. The speculation would be, for example, because you impacted this carbonate-rich terrain, instead of having a reduced fireball, your fireball is full of CO2, and so it's very oxidizing. So the iron never got reduced. And, we just say, well, we're having a different kind of target, so the tectites are different. But, they would say, you can't get away from looking at that ratio. Tectites aren't that way. And so those are the sorts of arguments they would offer. In terms of Chicxulub, the argument goes, this can't be a KT boundary crater because those late Cretaceous rocks occur on top of the breccias. Of course, we showed the one sample we had wasn't late Cretaceous, in fact. but they repeated what was in the old report saying late Cretaceous rocks occur. I mean, I would have thought it would be reasonable to withhold judgment until you have new samples, which will, of course, settle the question. There's something about the whole tenor of the debate that I really don't understand, though. I mean, I would think we've got to the point now, if we were in business, people would be charged with fraud by now. In the scientific world, it doesn't work that way. I mean, it's a question of opinion. And I honestly don't know. Suppose you go down here and you drill this crater, you put a couple of holes through it. In fact, you find that the biostratigraphy says that the base of the tertiary rests on top of the breccias. You go all the way through the breccias into the melt rocks and so on, and everything checks out. Everything is as you predict for the crater. In fact, of course, I predict ejecta thicknesses all over the place now. On another dozen localities of thick ejecta have turned up in Mexico, which more or less fit the prediction. What will they say then? And my feeling would be that the argument will not stop in some quarters. It'll simply be one of those cases in science where it goes on forever. People will say, there's some reworked Cretaceous bugs, for example, in the tertiary fill in that crater, and they'll say, well, see, there's some Cretaceous here. It is late Cretaceous. I told you. I mean, it's reaching a level of grasping at straws.
Was G2 Club a solitary event, and were secondly two others, and you looked into those two others?
All the evidence we currently have is consistent with having just one crater. Now that doesn't preclude that 3 other objects hit the Earth at the same time while a band of angels played on. I mean, one can postulate things endlessly. All I can say is I don't see anything in the evidence that requires other simultaneous impacts. Now some people argue differently. For example, there's 2 layers in the western interior of the United States. Some people say those 2 layers represent 2 separate impact events. I just think they're different dispersal mechanisms for the material. I mean, some people are even trying to there's a crater in Iowa called Manson. It's only 35 kilometers across. Some people are still trying to say that it's the sole KT boundary crater, and that all this thick ejecta to the south is just a local reworking effect or something.
There's also one in Siberia.
There's one in Siberia whose age is much younger. It's 35 million years, but someone pushed a bad date far too hard. There is another crater pair in southern Russia near the Black Sea called the Kamensk-Gusev pair, which in fact is quite close to KT boundary time. And I mean, indeed, you would want to know the ages of all these craters to answer the question of, this was probably a comet. Was it a part of a comet shower? And so you want to know if all these other craters, in fact, are quite different in age or quite close, but simply because error bars in the dating, show it could be possible. They could still be 2 million years different and completely different. And from the normal statistical reign of craters on the Earth, I mean, wouldn't be anything unusual at all. They have to be within, say, 500,000 years of this event for them to be related in comet shower. And the only way I think you're going to be able to tell this is to go to one of these other craters, like the Iowa crater, and find its ejecta in a sequence with biostratigraphy, with the KT ejecta and with its ejecta, so you can see exactly how much stratigraphy separates them. That has not been done. Yes?
Well, I've got a couple of comments to make first, and I'll ask a couple of questions. The first one is actually, it's actually been on the internet, a report of a lecture about cometary impacts in Boston a few weeks ago, in which somebody was complaining that the Canadians had gone charging around looking for craters across the Canadian landscape, and they wouldn't let all their data out because it was important, because you often find oil in the tracks and various other tracks, rocks and stuff like that. Meteorites. Whether that's true or not, I don't know, but that was on a lecture that was given at MIT about 2 months ago. The questions were, one of which, as you said, is it hit a bed that must have had quite a lot of anhydrite in it.
Is observed to have a lot of anhydrite.
Okay. In which case you're getting sulfuric acid, which means you're going to get sulfuric acid droplets in the atmosphere. Has anybody put these into a model? Because that's very reflective. That's
Sure, yeah. Sigurdsson et al. Attempted that, and as you'll see in the current issue of EPSL, they do some back-of-the-envelope calculations about the consequences of that.
And the other question is, was there any, since it was in water, was there any wash back I mean, you make a crater.
Right.
Did the ocean flood back in? Was there any washback after this?
Into the crater itself?
Into the crater.
Inevitably, the crater deposits must have been modified by this washback. So there was the question about why is the northern third truncated. It could be, in fact, that most of the water came in from the north side, and maybe that modified the northern third of the crater. But I mean, I don't know. It's one of those situations that, you know, it's time to go out and get some more data to answer these questions rather than speculating too much about it. There was a question back here. Yes?
Is there any evidence which supports this theory of an unusual distribution of plant or animal-like area of the crater? For instance, this huge wave which would have been created by an impact should have distributed plant and animal matter far away from the surfaces normally seen.
No evidence of that. Various people have thought, well, gee, close to the impact site, the thing should have been hit harder than far away. But obviously effects like the acid rain, the global dust cloud, are going to be global. Otherwise, of course, global species wouldn't go extinct. Of course, very close to the impact site, I mean, if the thing lands on top of you, you're going to be dead. Very close to it, I mean, everything's going to be heated to a great temperature. And so the death rate very proximal to it is going to be total. But unless you're a species that only exists in that small area, you know, some members will continue elsewhere. And so I think there will be some regional gradients found eventually, but you'd be surprised how little we actually know about the fossil record and so on. For example, the Asian continent, I mean, in North America, things are an order of magnitude more worked out in North America and Europe than in the Asian continent. And it will take a lot of time to do, you know, all the basic biostratigraphy. If you're a palynologist here, you study spores and pollen. Everything in India, for example, is different. And so it takes a lot of time to, you know, set all this up. I mean, that's a 20-year project.
Were there mass extinctions in the ocean as well?
They were most severe in the ocean. And it's interesting when you think about it. You say, well, gee, the ocean's a great big place, so something that lived in the ocean should be better off than something that lives in a freshwater lake. Lake's a small thing, could easily be destroyed. But it turns out you're better off if you're living in a lake. The reason is there's the same flux of acid rain all over the earth, let's say. If you're a marine creature living in the surface layer of the ocean and the pH changes enough to dissolve your carbonate shell, you're gone. I mean, that's how much acid we're talking about here. But if you're on land, most of the lakes, of course, are going to be wiped out by this acid rain too, if they're on granitic terrain, just like with acid rain. But if you're in a lake that's on a limestone terrain, it's going to buffer all this acid and it's not going to bother you at all. So simply because the lakes are small, I mean, the ocean is so big, I mean, there's no buffer there. There's nothing to buffer it. But if you're in that one lake in 100 that's on the limestone terrain, it's not going to bother you at all and you're going to live through the event. So small is beautiful.
Have you done any models for how massive the acid rain was, what its content would have been compared to?
10 to the 19 grams of SO2 from hydrating to form sulfuric acid.
How would that have washed out of the system?
It would rain acid.
No, I mean out of our system.
Oh, you mean once it's in the ocean?
Yeah, once it's in.
Oh. The waves on the mix the surface layer of the ocean to a depth of say 50 or 100 meters on, you know, this is on a short time scale. Say if you've done something in the surface layer of the ocean, it'll take it something like 50 years before that layer of water overturns with a deeper ocean. So you can upset the chemistry in that surface layer, and then, I mean, given time, of course, it mixes with, you know, the rest of the water column, which is 4,900 meters thick, and of course effectively buffers, you know, most of the effects that happen to the surface layer. And of course normal mechanisms, I mean, our sea has probably been the same salinity for a long, long time. The chemical and biological precipitation mechanisms that normally put sulfate and carbonate, you know, into sediments in the seafloor would restore the balance, and I mean, Earth obviously continued living. The biological feedback mechanisms are very powerful in this matter.
Of course, we know from radio astronomy of particularly comets like Comet Levy a few years ago that HCN and methyl cyanide are rather abundant in the volatile comets, of the order of a few tenths of a percent, possibly. So we could be talking about something of the order of 10 to the 15 to 10 to the 16 grams of cyanides entering, which would have a rather severe effect in the ocean.
This was suggested a long time ago by Ken Chu in 1980, in fact. But the problem with it is when the comet comes in, it turns to vapor, and all those molecules go.
Oh, right, yeah.
There's only like 1/10,000th of the mass tops that would fall off the back and would survive, so I don't think, that's been suggested, but I don't think it's going to be a big extension of the mechanism. I should also say, I meant to say during the talk, but I forgot, how probable is this of happening again? And obviously, an impact of boat this big happens on the Earth about once every 100 million years on that order. And of course, something this big, I mean, you don't need, to be very difficult for us. You're all aware of the Tunguska event in 1908. It was, I don't know, I think people are talking more 50 megatons now instead of 500, but it knocked down trees for something like a 30-kilometer radius, let's say. Obviously, if it happened where many people lived, a great many people would die. And events like that happen, well, some people would guess about once every 300 years now, though it may be more like once every 100 years. The threat as perceived by studies NASA's done, and they just released one in April, is an object that's big enough to raise the global dust cloud. In other words, it could land in Iowa or wherever. Of course, very close to the crater, things are going to be very bad, but once you get 1,000 kilometers away, it's going to be a so what. It will be a bit of an earthquake and nothing more. But if it's big enough to kick enough dust into the atmosphere to make the atmosphere effectively opaque, again, you're going to have this 2 months of darkness, say. And the idea is that's going to knock out agriculture, period. And we don't have the food stored. We probably have it in Canada or the States, but most of the world does not have food stored to miss a growing season. And so, what size asteroid will cause 1 billion people to die from disrupting agriculture? And the guess is, it's uncertain, we don't know exactly, but that will happen about once every 500,000 years. So when you work out all these numbers, I think it works out to effectively, each of us has something like a 1 in 6,000 chance of dying in an impact. Which, you're incredibly safe for flying in commercial airplanes. I think your chance of dying there is something like 1 in 1,000,000. It's like a surprisingly big number compared to, other risks we spend a great deal of time trying to avoid. Can you do anything about this? And obviously, if you know the object is coming, there's a great deal you can do. If you find it 20 years ahead of time, you only need a little push, it's going to miss the Earth. But nothing has been done in terms of augmenting the search for Earth-crossing asteroids. Of course, the short period comets you can do something about, but any comet can come out of your cloud effectively and have your name on it, and you'll only know about it 3 months ahead of time at best, say. And if it comes out of the sun, it could be considerably less. It's still conceivable that something we haven't seen, of this size is coming, but obviously it's a very rare thing. And of course, NASA is pushing to commit, I think it's something like $10 or $15 million a year, setting up a network of a half dozen Schmidt 48-inch automated asteroid comet searchers around the Earth. That's comparatively modest funding, as you all know, but it hasn't happened yet.
I have a question for you. You notice that at Tunguska in the East Siberia, there the terrible wave, the atmospheric wave.
Right.
Well, now in the Yucatan one, there must have been something like that that would probably knock all birds for 10,000 miles or something. In other words, a terrible, you showed the waves, the water, but there must have been an atmospheric sort of a sonic boom or whatever you want to call it, a terrible bang that would, a shock wave that would throw birds out of trees and things like kill a life that way.
The expectation is that what would limit it, in fact, would be the curvature of the planet. In other words, this impact would blow off everything
Tangentially, so.
tangentially to the planet. I mean, this painting of dinosaurs is obviously artistic license. I mean, by that time, by the time the wave hit there, it would already be pitch dark. And one of the more spectacular effects is, you know, a meteor is several thousand degrees. I mean, this ejecta layer that I was showing you pictures of in Colorado, Wyoming, Alberta. I mean, if you go out to the GA this summer, there's a field trip to see this layer in Alberta. This layer is caused by these 1 millimeter beads re-entering at the surface. They re-entered at the surface of the atmosphere. And of course, there's a layer this thick. And so after this impact, when this ejecta started coming down, the entire sky is going to be carpeted with this re-entering debris. The sky is going to be at a temperature, an effective temperature of, say, 1,000 degrees. Of course, the equilibrium temperature on the ground is 1,000 degrees. I mean, there's going to be a tremendous thermal pulse delivered to the ground near the impact site. I mean, effectively, North and South America are going to burn to the ground. Once you're farther away, the ejecta layer gets very thin. It keeps falling off thickness. By the time you get to Europe or farther distances, the layer is a millimeter or less thick, so the thermal pulse is not going to be sufficient to burn the comets to the ground. But North and South America probably went. And in fact, some of you have probably been to forest fire burns. Of course, right after the event, they're very smoky nothing there. If you go back to next year, the only thing that grows next year pretty much are ferns. They're the recovery flora. If you go to the layers, like in the Breton Basin, where you have the fireball layer, and then this cold layer overlying it, you take the basal millimeter out of that coal that sits right on top of the fireball layer, you'll find that it's 99% fern spores, and all the same species. I mean, it's the classic recovery flora.
No further questions? Well, I'll call on Robin Molson to thank the speaker now.
Dr. Hildebrand, your talk, which I thoroughly enjoyed, it reminds me of two things. You all know who Damien LeMay is. Many years ago, I guess you'd call it, back in the early 1980s, Damien called me one afternoon. I was over in Tadoussac and he was in Rimouski. He said he wanted to research some meteor craters up near Manicouagan, near Manic 5. So off we went. I drove down from Tadoussac. We flew over to Baie-Comeau, and we went there and drove down about 200 kilometers. And we had shovels and picks, and we had cameras and heavy boots, and we headed off into the woods with a compass and fly oil. And we had, this site was identified to Damien by a friend of his who was a hunter. And we went in with this instrumentation, you might call it. We found the site. We had a great deal of fun, and it was a long while getting there, but we found the site. Of course, it wasn't a meteor crater, it was an old moraine. But the difference between this little expedition and your discussion is profound, but the objectives, I think, are the same. And this makes a very telling incident for me, because of course I'm no scientist in that sense, but I did thoroughly enjoy this little outing, and I know exactly what you were doing in a much more sophisticated way. The other thing was when I was at school, back in the, well, I wouldn't even say when, it was late 40s, I guess. A theory at that time that was coming forward was Dr. Wegener's theory of the movement, the drift of continents. And at that time, it was very controversial. There were no instruments to prove it. There were no lasers, and there was nothing like no satellites or anything to measure the movement, the drift of continents. And we were looking at that time at McGill University in very much the same way that I think we're looking at what we've got here. I'm talking very, very broadly. The first I heard of the Iridium Layer was probably one of those small articles in Sky Telescope. There's about 2 pages of little snips. Back in about the late 70s, that somebody said they found iridium in Italy, I think was one of the countries, and there were several others. And that therefore, this showed that there was a possibility of a meteor or a comet contact with the Earth, which had made the dinosaurs and other things extinct at the time. But there were years and years after that that the theory of continental drift was finally accepted, and I think it is accepted now. And I think to a great extent, the same thing applies here, where we've seen a magnificent display of an attempt to prove something which somebody with a great deal of imagination and a lot of knowledge has put together. And I think it's fascinating. And I think eventually, judging by the sort of work that Dr. Hildebrand's doing, this will be proven if we get people like Dr. Hildebrand continuing their work. And judging by the color of his hair, he's got a lot of time left to do it. We have, it is fortunate and unfortunate in a way that in science, you come up with a theory, and for the next 30 years, everybody is beating it back and forth and saying, no, it can't be this way, it's got to be some other way. No, I found this, it can't be this way. This is how it all develops. And it's just what's really so fascinating about it. It keeps people on their toes, keeps people trying to go a little further than the other person, and they keep ahead of it. And I think that whatever it is, but maybe it's some of Dr. Hildebrand's maritime heritage, which I have spent a good deal of time down there, and I know a little bit about it. With this has made him very persistent, and I think the impressive talk he's given us, the proof, the lengths to which he has gone to prove his case, and to study to study the various things he's found, and to use his head to find out more things, and to go from one thing to another. I mean, it just seems as though everything's covered. But somebody somewhere will come up with something else, and he'll be ready to come back with another answer to that question too. So I think what we've heard tonight is a really magnificent account of this process in action. And I certainly want to thank you very much for a fascinating talk. And I hope you'll come back and talk to us about it again. And I wish you, and we all wish you all the luck in your future work in this area. Thank you very much.
Quaggan is about 210 million years old. There's one, it's 90 kilometers across, and there's one in the Soviet Union, Papagai, which is about 35 million years ago. It's 100 kilometers across. Neither of those is associated with a mass extinction. So the assumption is that a crater, or I should say no known mass extinction, is no definitely. So the assumption is you need a bigger crater to do the job. And of course the Chicxulub impact was particularly deadly because rather than just hitting metamorphic rocks or granitic rocks, it hit this very thick, many kilometer thick sequence of carbonates and evaporites. So in addition to being a big crater, it was able to release all the CO2, it was able to release all the SO2 to make acid rain, and by chance, hitting that thick a sequence on the surface of the Earth, you'd only do it maybe 1 in 20 times. So it makes Chicxulub, a 1 in a billion year event possibly, rather than 1 in 100 million year event. Sorry, I promised.
Looking into the future, do you see any possible defense against such collisions?
Well, if you knew one was coming down, and if you knew some, in enough time, you could easily go to it and move it. I mean, if you know it's coming down 10 years ahead of time, you only need to give it a tiny push sideways and it'll miss the Earth. And that, of course, is your protection. I mean, if someone discovered one is going to hit us a week from now, I mean, you could, I don't know how capable the missiles are, but I mean, even if you launched everything at it, you wouldn't do much to it, because in the vacuum of space, you explode it next to it or whatever, and you're just going to make a dimple on the surface, or Or perhaps worse yet, you'll break it up and you'll have a whole bunch of pieces coming down the whole side of the Earth, rather than, just one that's only going to damage one part.
So a well-directed massive nuclear explosion wouldn't be much of a defense.
Not on the short time scale, not for a big object, no way. I mean, you need time, you need to know that it's going to come. This study that NASA did, I mean, the idea was, what can we do, setting up an observing program to find these things. And it turns out, if you set up, 48-inch or 72-inch Schmitz, you have an automated system for scanning similar to what Spacewatch has, or what, the geoid system does for tracking satellites. You could find, I think, something like 95% of the greater than 1 kilometer population, the dangerous population, in something like 20 years. And it would cost you something like $20 million a year to do it. I mean, it would be a comparatively modest effort. Of course, you'd learn a great deal about asteroids in the process. But, I mean, this report was released in March. And, I mean, I haven't heard that anyone's been making presidential statements saying we have to do this. Who knows how it will fare.
Yeah.
You showed data that indicated the gravitational anomaly was truncated, but the magnetic one showed a complete ring. Do you have any speculation on why this might be, why that might occur?
Okay, 2 speculations. One, there was some sort of fault crossing the Campeche platform there, and the northern half down dropped a little bit. And in fact, there's a little evidence in the seismic reflection profiles to say that that might have happened. Now, if that happened, the sedimentation patterns and so on in the north might have been different, and you could have had different enough sediments to mask the gravitational signature. Another possibility, perhaps, when this impact occurred, we had a shallow shelf sea, say 100 meters deep or 50 meters deep. Perhaps, of course, the sea would be driven away, and then you're going to be left with this great big hole. And then, of course, the ocean is going to come pouring back in. And the deep water lay to the northwest. So it could be that, the backwash that filled the crater came from the northwest and, poured over that rim so strongly and so on that, it transported enough stuff to hide the signature of the crater, whereas in the rest of it, it wasn't disturbed. I should say there's also a possibility that we don't have the gravity sampled as well on the north side. It could be that with more detailed surveys, there will be some subtle effect that goes all the way around, although not necessarily as clear as we get on the plan. I see you next time.
If there was such a mass extinction, how do you answer the challenges of how we've ended up with reptilian forms similar to pre-extinction times and mammals that may have crossed? Is mass extinction not to be interpreted as total extinction, or what?
Well, extinction is the extermination of one species. Mass extinction is termination of many of the species, say half the species, or 20% of the species. Obviously, if all life had died, we wouldn't be here. Not if all life died, much of life died. I mean, Dale Russell would estimate something like 70% of the species extant died. Suffice to say, amongst the other 30%, there was probably mass mortality. Most individuals in the species probably died, but of course, in theory, if 2 of appropriate sexes made it through, the species could continue. I mean, most things probably suffered. The key to survival, I mean, you can speculate on this endlessly. For mammals, I mean, mammals were itsy-bitsy little things. They lived in holes in the ground. I mean, they could get away from most of these effects. I mean, if you were, a Tyrannosaurus rex, you were a big thing. You needed to find a lot of food every day. And, I mean, if it was pitch dark, and it was acid raining on you, and all these other things were going on, I mean, it was hard to do that. And so, if one little mammal found one dead Tyrannosaurus rex, he was probably set. And this is just a function of size. You can imagine that small animals had more places to hide, and it was easier for them to find enough food to make it through. So on land, it seems like the big things went extinct. And by the way, the same thing in the ocean to some extent, all the big marine reptiles. Now you say some reptiles did make it through, and that's true. I mean, turtles made it through, crocodiles made it through, and so on. But they were greatly reduced as well. For example, amongst the crocodilia, I think 6 out of 7 genera went extinct, which, I mean, that's a pretty nasty extinction for that, group of animals. But, I mean, the other genera made it through, and of course it's radiated to produce the reptiles we have today.
would the effects have been different had the morphology been different? Say this had hit into something like the Marianas Trench or something, extremely deep ocean, or the morphology where it hit was different.
I think changing target types does produce different effects. Obviously, if you hit in the deep ocean, I mean, this was a shallow ocean, so the waves directly from the impact site were small. We assume the bigger waves were generated because seismically it was the equivalent of a huge earthquake, and we assume around the edge of the Campeche platform there were huge submarine slumps, and these slumps created the giant waves. If you hit the deep ocean, I mean, you're going to have the huge waves. I mean, waves that big are going to make it all over the globe rather than merely occurring between North and South America, so there'll be more effects that way. On the other hand, oceanic crust, just basalt, is not a particularly deadly thing in and of itself because there's no CO2 involved, there's no acid involved. You're obviously going to vaporize a great deal of water and pump into the atmosphere, so you're going to have a rain of unprecedented proportion. But the water vapor will produce a greenhouse for a while, but it'll come out of the stratosphere, say, in 5 years or so. That's about the mixing time. So the greenhouse you get is shorter, but you obviously have different effects. I mean, if I was going to say, you know, if we had a choice in where to let it fall on the Earth, I mean, I would pick something like the Canadian Shield, simply because it's far from the ocean. You could pick a chunk that's just crystalline, granitic, or metamorphic rock, so you weren't going to get any CO2 involved, any SO2 involved. In a sense, that would be, I think, the safest sort of place. An ocean would be worse. Carbonate, evaporate, and so on would be worse.
You carry a lot of work.
That's all a lot of problems.
Could you explain why the platinum-type elements would be are relatively rare on the surface of the Earth?
It's because if you added up the whole Earth, you'd have the same abundance of platinum group elements as you have in meteorites, which are undifferentiated. Far below our feet is the Earth's core, which is native iron. And given a choice, platinum and all the other platinum groups will go into the iron rather than into silicate rocks. So when the Earth first differentiated, all these elements went into the Earth's core, and our crust is stripped of these elements. Abundances in the crust are 1,000 times less than in meteorites or in the bulk Earth.
Yes, I attended a lecture by the other side of the story at one time, and the objection they had was in the time frame. They felt that there was 9 layers down with iridium over 1 million years. How would you address that problem?
Imagine, in fact, that this iridium-rich dust had just finished falling on the surface of the Earth. And so, you know, we have a layer 3 millimeters thick all over the surface of the Earth. And now we have 65 million years to screw up this beautiful, pristine signal. How are we going to do that? I mean, one thing we can do is we can start reworking it. You know, we'll erode it one place and we'll dump it someplace else, and so we'll make it thicker at this site. Another way we can do it is we can have organisms, you know, dig through it, make burrows and so on, what we call bioturbation, and it'll stir up the iridium into the sediments below and the sediments above. And in fact, I mean, I've seen deep sea cores like 690C, where you have the iridium-rich layer, and you can see a burrow 90 centimeters below that, full of the iridium-rich layer. And I mean, that organism just took it down there. And, you know, so what? I mean, that's just a mixing effect we can see. Now, additionally, we took all this fine dust and we're going to alter it. You know, it's fine in crushed rock or glass particles, and we're going to turn it into clay minerals. We're going to change its you know, chemical composition and structure, so the iridium has a chance to be mobilized geochemically and transported by solutions above and below. We're going to have tectinus in some places. We're going to have some parallel sliding along these beds. So I'm going to be moving chunks up and down. So all those things disturb this original spike of iridium and broaden it effectively. I mean, it's no great trick. People have done this. You can go to an oak crop, for example, as Doug Nichols did in Wyoming, found a KT layer, and he sampled across the layer, and he got an iridium anomaly that, you know, the iridium was spread out for this much. He gave these samples to Carl Orth. Carl said, well, this is pretty broad. He went back and he dug a meter into the hillside to get less weathered rock. And just in doing that, he got the iridium spike down to this wide. That's just because surface weathering broadened it geochemically. And so I would say that, you know, all the sections I've seen, there have been various things to perturb the signal, but I certainly, you know, I believe it's just because of secondary disturbances to the original signal. There was a question here.
Is there any work being done on the big semicircular, well, not home, the semicircular up in the East Coast of Hudson Bay where the Dutch Islands?
Oh, I mean, everyone who's ever lived impacts, thinks, gee, that sure looks like an impact crater. And various people have gone there and looked at it, looked for impact wedges or shatter cones or other signs of impact. No one's found a thing. And so, I mean, the matter remains, well, gee, that's a pretty circular feature, but there's no evidence of an impact. And some people have theories that it's a something else. And I mean, that's literally where the matter rests. No one's found any evidence of an impact there yet, except that, boy, it sure is circular.
Subsequent to the impact, when sedimentary material was brought back into the crater site, was there a lot of breccia brought back in, or ejecta?
I would imagine that the backwash that filled the crater would have, disturbed the ejecta blanket near the rim and so on. We just don't have enough information to know exactly what happened then. I mean, obviously, knowing where the crater is now, I mean, you'd like to go down there and you'd like to do more surveys, you'd like to do seismic reflection studies, you'd like to do more drilling, and, see what you can do to answer all those questions. Suffice to say, this will probably happen sometime. We're trying to set up cooperative ventures with the scientists in Mexico who are interested in this, and that's just an ongoing process.
What's your evidence for a comet as opposed to an asteroid impact?
It's actually quite elegant. When you go to a site, any site where you have the fireball layer, I mean, you can analyze across it and see how much iridium you get. You can make an integrated column abundance, or affluence of iridium. And it turns out at any one site, that number is about 50 nanograms of iridium per centimeter squared of the Earth's surface. So you figure out how big the Earth is. The KT boundary layers have about 250,000 tons of iridium. That's what the projectile brought in. And knowing the concentration of iridium in asteroids from meteorites, you can say how big an asteroid would bring in that much iridium. And the answer is, for an ordinary chondrite, an undifferentiated asteroid, an asteroid about 6 kilometers in diameter. For a nickel-iron asteroid, about 3 kilometers in diameter. And for asteroids, because they go around the sun the same direction as the Earth, they can't hit the Earth very fast. The average impact velocity is about 25 kilometers per second. And you can figure out the energy a 6-kilometer asteroid going 25 kilometers a second would dissipate. And you can figure out how big a crater it would make. And the amount of energy is about 100 times less than the amount of energy that was expended in making the Chicxulub crater. And so you say, well, gee, asteroid doesn't do a very good job. So you think, well, what about a comet? And comets, you know from estimating mass, dust tails and gas tails, or from the Halley flybys, that the silicate proportion of a comet is about 10% or less, the rock dust, the dust that's going to carry the iridium. So as soon as you go to a comet, you can get 10 times the mass for the same amount of iridium. Now the other thing about comets, of course, is they can be retrograde, like Halley. You can have them go in the other direction so they can hit the Earth going as fast as 72 kilometers per second. Because energy is, kinetic energy, 1/2 mv squared. That squared term on the velocity, the average impact velocity for a long period of comets is about 60 kilometers a second versus 25 kilometers per second for an asteroid. That buys you another order of magnitude. So, a big comet, as we understand crater scaling relations and so on, will make a crater as big as Chicxulub and give you that amount of iridium, whereas an asteroid fails by a factor of 100. This one. Oh, sorry, you already asked it all. Go back to him, sorry.
How do you find the mass of a comet, and how do you know how much iridium is in a comet?
You know the amount of iridium in a comet through the simple assumption that all silicate material in the solar system has iridium in it. And you assume that comets are undifferentiated, as the undifferentiated meteorites are. You go to the meteorites which are most comet-like in composition, the C-ion chondrites, and you extrapolate from that. And as I say, from the Halley flybys, or from looking at the tails of comets, you know the dust to gas proportions and so on. So that's how you know how much iridium is in a comet. Though I'll grant you it's in this assumption known as a sample of comets.
It is an assumption.
Well, I mean, I'll defend it, and, I mean, this is one thing that, I mean, no one chases me around for saying that at meetings, so it's... No, there's a second part to your question.
The mass of the comet.
The mass of the comet. Well, again, given so much iridium in the boundary plate, 250,000 tons, and assuming a composition of iridium in a comet of about 40 ppb, you get a comet of about 10 to 19 grams to produce, to supply that much iridium to the Earth's surface. I guess you get to ask your question.
The question of acid rain, both from sulfur compounds and nitrogen compounds, is very interesting. Has there ever been any evidence, or are you aware of evidence of alteration of the first layers, let's say in association with either the ejecta blanket or the top layer, or even of the tertiary or Cretaceous, excuse me, that might indicate alteration due to this acidic atmosphere?
That's a good question. Ejecta Layer in 1987 suggested that, in fact, the uppermost meter or so of the Cretaceous in the western part of North America did show some unusual effect, which might have been due to the acid rain leaching. And he said in particular that in the very last meter of late Cretaceous, you don't often find dinosaur bones. So he suggested you don't find dinosaur bones in the last meter because of this acid rain effect leaching the phosphate out of the bone material. And I don't know that, that could be. It's plausible, but it's a tough one to prove. At Brazos River, there's an unusual micrite, which I have speculated might be due to, the acid rain dissolving all the carbonate organisms. And of course, as the stuff is remixed, this carbonate would be precipitated chemogenically, and you get an unusual abiogenic micrite, which in fact you have at Brazos. Again, that might be, but again, that's a tough one to prove. Yes?
An earlier question about surface features, and one thing I read about last year was the so-called cenote ring.
Right.
Which you did mention. Could you say has that theory been refuted, and that's why you mentioned it, or has there been any further development on it?
Now that's related to the slide I showed you. Remember I showed you the fracture patterns that showed a subcircular ring? The groundwater, the fresh water on the Yucatan Peninsula is a thin layer, 100 meters to 50 meters thick, that flows from south to north. It flows north, and then it is flowing through those fractures preferentially, and then it hits that semicircular ring. And of course, once it runs out of fractures, it preferentially runs around the ring of fractures. And it's the groundwater preferentially traveling on that zone that makes the cenote ring. Because there's more groundwater moving there, it makes solution, caves, and they collapse and you get cenote. So that cenote ring is just tied into this fracture pattern, which I did discuss. And I mean, it's certainly, simply by coincidence, it seems likely that somehow the different rocks in the crater were influencing the mechanical response of that part of the world, and so that fractures were developed outside and not inside. And the cenote ring is the symptom of the fractures being that way.
Given that that's still a viable theory, then I wondered, since sea level, of course, has been reducing a number of times in the last number of years, could the cenote ring in fact extend well offshore?
I would assume so, yes. But obviously, it's not mapped in sufficient detail to say.
I think we'll call the questions to an end. If you wish to talk to Dr. Hildebrand any later, you have to stay here. Thank you for your questions, and thank you, Dr. Hildebrand, for your interesting answers and for a very intriguing lecture. And now we have to do some nice and nasty things to you. And in order to do that, I have to become Western. Bill Peters would not let me bring my horse in. Other than that, I am what we refer to as Deputy Chief White Hatter. Because I'm just a deputy, my hat's not white. And we're going to make Dr. Hildebrand an honorary Calgarian. And I have to read this. It's quite cute, actually. This here paper proves Alan R. Hildebrand had the purely pleasurable experience of visiting the only genuine cow town in Canada, namely Calgary, and was duly exposed to the exceptional amounts of heartwarming, handshaking, tongue loosening, backslapping, neighbor-loving Western spirit, is hereby deputized as an honorary Calgary White Hatter. Said title means from this day on, the owner of this certificate accepts responsibility for extending this brand of Western hospitality to all folks and critters. Give you an official white hat with 2 GA pins.